started here. So we're going to finish chapter 2, and next week we'll start chapter 3, I guess. And so I feel like there's not that much to do today, but it is a lot of concepts, so you will need to go home and practice it, right? Once we've gone through the example, I think you'll see what I mean. But we'll start with just a quick review. We did, and this was just, this was just on Tuesday, so not that long ago, right? But we talked about proportions and percentages. Ratios were in the title, but we didn't really talk about ratios that much. Proportions and percentages. We also talked about, so then we moved into chapter 2 where we started getting into potentially some new stuff, where we said, okay, we need to be able to draw a straight line, right? And so we talked about how to draw a straight line given an equation, of course. Right, so if you have an equation in the form y equals mx plus b, then you pick two values of x, figure out what the values of y would be at that point, plot those points, connect the dots with a straight edge, and then you've drawn your line, right? And we talked about functions, just what are they? Functions, which also included the domain and range. So today we're going to start section 2.2, which is supply and demand economics, which you've likely seen in other courses, right? Or at least kind of heard someone mention. So let's get that down here. So supply and demand economics. I'm not going to get into, oh, there was a shortage of glue and so the paper prices went up. I don't pretend to have my head wrapped around that. So we're just going to talk about the math bit, right? So let's just talk about some basics here first. If we've got a graph with the price on the y-axis and the quantity on the x-axis, your demand curve is usually denoted by a capital D at the end. Your demand curve is always going to have a negative slope. If the price is high, we don't want that many. If the price is low, we want more, right? That's the demand curve. And so the demand curve has a negative slope. And same idea, we've got price and we've got quantity. The supply curve is going to be going up, right? If the price is low, I don't want to supply that many. If the price is high, I want to supply a lot. Right? And so the supply curve has a positive slope. So these two cross, right? And that point of equilibrium is where the points intersect, right? And so that's where the sweet spot is. And so the point of equilibrium, is the point of intersection. So we have something that looks like this. Same idea, we've got price and quantity. We've got our supply curve, but we've also got our demand curve. This point here, do it in pink. That's equilibrium. Which means at this quantity and this price, everyone's happy, right? And so that's a happy market. You'll never hear that in economics, I don't think. A happy market. But you will hear, right? So I hear everyone's happy. And we usually denote it by a P and then subscript EQ. You don't have to know that, but, and then a Q subscript EQ for equilibrium. The supply and the demand curve are straight lines, right? And so we know that they're gonna have the form y equals mx plus b. Right? And so, since S and D, right, the supply and demand curve, just kind of shorthand, are linear equations, we can solve the system of equations to find that point of intersection, right, to find the equilibrium, which we know how to do already. We solved systems of equations not last day, but the day before, right, either by substitution or by elimination. Remember those, right? Those, we were solving systems of equations, and that's what we'll do here to find the point of equilibrium. So since S and D are linear equations, we can solve the system of equations to find the point of equilibrium. Sounds fun. Revelstoke, there's no snow yet. So, for example, so these are going to be set up a little bit different than what we are used to seeing, only because we're going to have a Q-axis and a P-axis, right? It's still the X and the Y-axis, but for these situations, right, supply and demand situations, we're talking about quantity and price, right? So we're going to swap out Q for X and P for Y, right? It doesn't matter which one's which, as long as you remember that they behave the same way. So let's do this example. Find the point of equilibrium. Find the point of equilibrium when the supply curve, so I'll just do supply, the supply is Q is equal to 2P. And the demand curve has the formula Q is 10 minus 3P. I guess you could use elimination. It doesn't really jive, right? But because they're both in terms of Q, right? Q equals 2P and Q equals 10 minus 3P makes it really easy to use substitution, right? Because then you can just substitute the Q from the supply equation into the demand equation, solve for P, and then you can solve for Q, right? So I'd say it's a little bit easier than before. Let's call this equation 1 and this equation 2, just because S and D are hard to reference them by. So what I'm going to do is I'm going to substitute equation 1 into equation 2, or the other way around if you want. It's the same thing, right? So then I get 2P is 10 minus 3P. Solving for P, right? I have to collect like terms, so I have to bring the P over to the left-hand side. And so I get 2P plus 3P is 10. So we get 5P is 10. P must be 10 over 5, so P is 2. If P is 2, well, we can solve for Q pretty easily, right? And so substitute P equals 2 into equation 1, or equation 2 if you want to have more work. So Q is 2P, so Q is 2 times 2, so Q is 4. Okay. So equilibrium is when the quantity is 4 and the price is 2. Right? For whatever object, we don't know. So the point of equilibrium is when Q is 4 and P is 2. So I always put a question like this or a couple of these on test 1, right? And they're meant to be really easy questions, but for some reason, I think you guys are in such a rush, or not you guys, but in the past, people are in such a rush to get through that you forget to solve for the other one, right? And so you'll only solve for P and then move on, right? But you have to solve for P and Q, right? So make a little note to yourself that you have to solve for P and Q, otherwise you haven't finished the question, right? Otherwise you can only get half marks, and that's no fun. Right. Any questions about that one? No. So it's just what we were doing before, right? Solving systems of equations, a little bit easier than what we were doing though, right? Because usually they're already set out like Q equals this and Q equals this, right? Or P equals this, doesn't matter. All right. Any questions? Moving on. All right. Section 2.3 is on linear programming. Like a baby version of linear programming, but still. I like this section because it draws everything together, So first we're gonna draw straight lines on a graph, so I get to see that you know how to do that. Then we have to solve systems of equations to find intersections, right, which is also something that we've been working on, right? And then we use those intersections to find the maximized profit. So it pulls everything that we've learned so far together. And so there's nothing really new except all the steps that we're doing to solve a problem. Okay. And one note is that some classes don't do it. I like to do it because then I can skip a different section that I really don't like. So you guys don't have to do that. So don't worry, you're not doing more, it's just doing different. Okay. This is a section that people have a hard time with, right? And so that's why I say it's not gonna feel like a lot when we go through it, maybe. But make sure you go home and you do the practice and maybe some practice problems out of here from section 2.3 after. Okay. So what is linear programming? So linear programming is what we have to use because often we have restrictions on things that that affect our production costs, right? And so maybe we only have 4 machines, right? If we had 1,000 machines, yeah, we could crank out as much as we want and sell them and sell them and sell them, right? But maybe we're limited by machinery, the number of hours in a day, right? Maybe it takes a long time to produce something, right? You're only able to produce 20 units in a day, right? And so we have these limitations, but we still want to maximize our profit, right? And so linear programming is used to maximize our profit given the limitations that we have. Okay? So we often have restrictions. We often have restrictions on our profit function. Things like time, materials, machinery, labor, right? Things go on and on and on, etc. All these things that could limit how much you produce, right? Linear programming will let us maximize a profit function. Oops. A profit function given a set of restrictions. So before I show you an example, I want to talk about the steps that we do, right? Because I think if we have a look at the steps that you're going to follow, it won't look as bad, right? And so steps to maximize a profit function. Sorry, I just heard that buzzing. It's obviously on the whole time, but it's better. So the first step is you're going to draw the restrictions on a graph. Now these restrictions are just going to be straight lines, right? So maybe you only have 4 machines and maybe you only have 6 hours that you can work during a day, right? That kind of thing. And so first step is to draw the restrictions on a graph. Okay. The second step is shade in the area that satisfies all the restrictions. Okay, this area is called the feasible set. Okay. So shade in the area that satisfies satisfies all the restrictions. All the restrictions. Usually what happens is we start in the bottom corner and we just balloon out until we hit lines. Right? I'll show you what I mean by that, but it'll be on YouTube. Don't worry. I hope you feel better. Third step we're going to do is we have to identify all the points of intersection and find what those points are. Okay? So find all the points of intersection. So find all the points of intersection. Okay. These points, right, are ordered pairs. Remember we talked about ordered pairs last day? That's when we write something like x comma y in round brackets. That's an ordered pair. So the next thing you're going to do is make a table of all the ordered pairs that you found in the previous step of all the intersections. So make a table of all ordered pairs from step 3. They're going to have an x and a y value. Okay? This is where your profit function comes in. So now you're going to evaluate the profit function at each xy ordered pair. Okay? Whichever one is the highest, that is the maximized profit function. Okay? And so fifth step is to calculate the profit from each of the ordered pairs. And finally, the largest, I'll put in brackets maximize, right? That's the same. Maximized profit is the optimal solution. So the one we're looking for. Let's do a basic one. But any questions before we do? So those steps are kind of not making sense now. It's okay, right? But we'll do this little example. So then you can see what these things will look like. So maximize profit equals 3x plus 4y. Okay, so that's your profit function. And then what does it usually say? Let's say restrictions or subject to. Subject to x has to be less than or equal to 4. Y has to be less than or equal to 4. X has to be greater than or equal to 0, and Y also has to be greater than or equal to 0. And so these here, these are your restrictions. This is your profit function, but these are your restrictions on your profit function. All right? And so we want to know, okay, what combo of X and Y is going to maximize our profit? Right? And so this one you can just look at and say, oh, 4 and 4 looks pretty good. Crank them up, right? But this is just to illustrate the procedure, right? And so what we do, right, if we go back here, is the first step is to draw the restrictions on a graph. Okay? So let's do that. So on a test, of course, I would give you these axes. Say 1, 2, 3, 4, 1, 2, oops. Yeah. One thing, X greater than 0 and Y greater than 0, those will always be there, okay? All that's saying is that, okay, well, we can't be over here in the negative X's, right? That would be things like negative machinery and negative time and negative labor. It doesn't really make sense, right? And same here, we wouldn't be down here in, negative, again, negative machinery or negative time. And so we're only going to look at this quadrant, right? And so that's what these two are saying. They have to be there because it is a restriction, right? But those will always be there. And so that's how you know that you can just start with just working in this quadrant. So you don't have to worry about negatives. So these are kind of defaults. This is your x-axis, this is your y-axis. Okay. So by drawing our axes, right, we've already covered these two restrictions in the bottom, right? And so we can we can check those off. That one's on there, this one's on there. X has to be less than or equal to 4. So what I'm gonna do is I'm gonna draw a line at x equal to 4 to try to make it as straight as I can. I don't know, it just changes my, I'm not that good at drawing straight lines. Okay, but so this is x equal to 4. If x has to be less than or equal to 4, right, that means that we're working on this side. right? And so all that's saying is that everything on this side of this line, and this line keeps going and going and going, right? Everything that's less than 4 is good, right? That satisfies the restrictions. Okay? And so what I'm going to do is I just draw a little arrow to the left saying, hey, everything on this side is good, right? Satisfies our restrictions. So that's that one on there. Same thing with y has to be less than or equal to 4. Notice that I'm treating it as an equal sign and then figuring out which area it's talking about, right? And so if I draw a line at y equals 4, right? Again, I need y is less than or equal to 4, right? And so everything y less than or equal to 4 is good. And so I'm going to put a little arrow here just to remind myself that this is all what I can work with. Okay. So here, what we have is we said, okay, well, we're bounded by these here. Okay? And as a rule, what's going to happen is you'll start down here in the corner, and to draw your feasible set, you're just going to keep sprouting out until you hit lines, right? And so your feasible set is everything from 0, 0 out until you hit lines. And so if we draw this like this, right? This area is what we call the feasible set. So any value, any XY combination that's in here satisfies the restrictions. Okay, so the feasible set just says any XY combination in the feasible set satisfies the restrictions. So we can plug in any combination, and we could do things like 1.7 and 2.3 if we wanted to. All those points are inside our feasible set, right? And so they're all allowed. And as a fact, and what's really kind of cool is that the profit will be maximized, right? So you'll still get profit at any point in here, right? But the profit will be maximized at one of the points of intersection, right? This is a point of intersection. This is a point of intersection. This is a point of intersection. And this is a point of intersection, right? All those points satisfy the restrictions, but just as a fact, the profit is maximized at one of those points. Okay. So here, fact, the profit is maximized oops, at one of the points of intersection. So if we go back to our list, I kind of forgot to look back on it, right? First step, we drew the restrictions on the graph, and then we shade in the area that satisfies all the restrictions. I'll put in orange here. This is the feasible set. Forgot to write that. I said it, but I didn't write it. So then, right, so we've done that. We've shaded in the area, right, that satisfies all the restrictions. Then you're going to find all the points of intersection. Okay? And what we're going to do is we're going to label them. For example, our first one that we'll always have is this one down in the very corner at the origin, 0, 0. So A is the point 0, 0. Okay. The reason I'm labeling them A, B, C, and D are because later on there's going to be intersections that we'll have to solve the system of equations to get to. Here we know what they are, right? So it's not that bad, but later we'll just label these. B, which we already know is at 0, 4. Call this C. And you can, as long as you're labeling kind of for you to keep track of, you can label them whatever you want, however you want. But I usually just start at the origin and work my way around clockwise. C is at 4, 4. And D is at 4, 0. Good. All right. The hard part's over. Because now, so step 3, find all the points of intersection, which we did, right? It might mean solving a system of equations, as we'll see later on, right? But for now, we've found all our intersections. That's good. Next step is to make a table of all the ordered pairs that we found, so all the intersections. And so we're going to make a table of the intersections. Intersection, and I'll say A, B, C, D, just so I can look back at them. A was at 0, 0, B was at 0, 4, C was at 4, 4, and D was at 4, 0. Okay. So now we've made a table, okay, of all the points of intersection, right, and the ordered pairs. Next thing we're going to do, right, is calculate the profit from each of the ordered pairs. Right? And so this is the first time that the profit function actually comes back into play, right? Because, oh, I guess I should check off, because we did take care of that one too. So we haven't touched the profit function until now, right? So it just hangs out until the very end when we're ready to plug in our X and Y combinations to see which one is the biggest profit. So we've got profit is 3x plus 4y. So what I'm going to do is I'm going to put that here. Profit is 3x plus 4y. Remember, the intersection, it's x comma y, right? So for the first one, we can calculate the profit as 3 times 0 plus 4 times 0, 0 profit. Makes sense, right? If you're not using any labor or any machines, you're not going to make any profit. It's fair enough. Right, but the profit is going to be 3 times 0 plus 4 times 0. for the first intersection, which is 0. Then the next intersection B, we've got 3 times 0 plus 4 times 4 is 16. 4 times 4 plus 0. That's better than 0, right? I have a feeling that 4, 4 is going to give us an even better profit, right? But let's try it. 3 times 4 plus 4 times 4 is 12 plus 16, 28. It is, right? 12 plus. Phew. 3 times 4 plus 4 times 0 is 12. Right? If we had started here, right, and I asked you, hey, which profit do you want? 28, please. Right? And so that's the one that we pick. Okay? And so I'll just highlight this here. 28. Our profit is maximized at 4, 4 at a profit of 28. Now we're not going to talk about units here. Units, it could be $28. It could be 28 million, right? It doesn't, we don't know, right? It doesn't matter. 28 million sounds good. But 12 million sounds pretty good too. Right? Yeah, nah. 0 million? Yeah, that's good. I guess we're all millionaires then. 0 million. Okay. So we'll do a bigger example, but so there are a lot of steps, right? But these steps are always going to be the same. And so if you practice these steps, right, then it's a pretty fun problem to solve. Okay? So any questions though before we go on to the bigger one? Bigger example? That one was kind of fake, right? A line here and a line here. Not that fun. So, all right. This is example 72 from the textbook, and it says maximize P, which is the profit, is X plus 1.2Y subject to 2x plus y has to be less than or equal to 180, and x plus 3y has to be less than or equal to 300. Yikes. We didn't sign up for this. I know. Right? But the idea stays the same. And of course, our default ones, x has to be greater than or equal to 0, and y has to be greater than or equal to 0. I don't know about you guys, but I used to have a tough time with inequalities, and I still do. Inequalities are these less than or greater thans, right? And so I always used to try to think of the alligator eats the big one, but that didn't really help me because it's just, yeah, I don't know, right? And so so then someone told me if you just take your fingers and make an L, right? So then this is less than, and so you read it as y less than 180. Right? If it's this way, then it's not less than, then it's greater than. Right? You only need to know one. Okay? So if you have a hard time with that, then give that a go. Okay? For most of our calculations, right, we can do what I did earlier, just treat it as an equal sign, right? Draw the line, and then figure out which side of the line I'm working on, right? And so here, we can treat the inequalities, the less than, the greater than, as an equal sign. Until we have to find our feasible set, right? Until we have to find our feasible set. Right, that's when we need to know, okay, do I want to be below this line or above this line? I have to mention too that if you multiply or divide both sides by a negative, then the sign changes. That's not going to happen for us. Okay, so it's not a thing that you have to worry about. It's just something I have to say and write down because it's the truth. Okay. If we multiply or divide both sides by a negative number, so it's only for negatives, by a negative number, the sign changes direction. Yeah. So like I said, that's not something that you're going to have to deal with or worry about, but it is a fact. Right. Okay. So our first step, right, is to draw these lines, and we recognize both of these are equations of lines. We just have to rework them a little bit to be in the form of y equals mx plus b. Right? You could use them in that form too. I just like to have them in the same form, y equals mx plus b, so that I can see it's a straight line. Okay? You could leave it like that and skip this step, but I won't. Okay? And so the first thing that I'm going to do is just change these or rewrite the first two equations to be in the form of y equals mx plus b. Okay. So I'll call this equation 1 and this equation 2. Okay. To simplify my calculations, I will rewrite equation 1 and equation 2 in the form y equals mx plus b. So for equation 1, for example, we've got 2x plus y is less than or equal to 180. So we want to get y on its own, right? Because we want this as y is less than or equal to some number. So we've got y is less than or equal to 180 minus 2x. Like I said, we can just treat the inequality as an equal sign. Do the same math. right. How about equation 2? Equation 2 was x plus 3y has to be less than or equal to 300. Trying to get y on its own, right? I'm going to subtract x from both sides, so I get 3y is less than or equal to 300 minus x. And then I have to divide both sides by 3, so we get y is less than or equal to 300 minus x over 3. I'm going to break this up, right? But I have to remember that the 3 is dividing both of these terms, right? And so we actually get y is less than or equal to 300 over 3 minus x over 3. So y is less than or equal to, I can rewrite this as 100, but the x over 3 has to stay x over 3, right? Or 1 over 3x. 1 over 3 times x, technically. Okay. So now they're in the form y equals mx plus b. Right? I know now that y has to be less than each of these lines, right? So I'm always going to be below on these lines. Okay. Now I want to graph these, right? And so we haven't drawn any lines lately, right? But we find 2 points on each of the lines, and then we plot those, and then we connect them. Okay. And so the first step, so step 1, that wasn't even a step, it was a pre-step, step 0, getting them in the form y equals mx plus b. Step 1 is to draw the restrictions on a graph. Okay. And so remember, I just make a table of x and y values. And so for equation number 1, I'll put 1 here. We found y is, and I'll use equals 180 minus 2x. So y equals 180 minus 2x. I dropped the inequality, but it's okay because on the line, right, the line that we're drawing, it is y equals, right? The restriction is that it has to be less than that, but the actual line is at y equals. Okay. So I'm going to pick convenient values of x. X equals 0 is always a nice option, right? So I'm going to start at x equals 0. And I find that 180 minus 2 times 0 is 180. Oh. Here's a note, right? Because I'm dealing with 180 minus 2x, if I just did x equals 1 as my next option, right? That's usually a convenient number, but it's going to be really hard to draw points that are that close together. Right? And so what I'm going to do is I'm going to use a bigger value of x so that I can have them kind of further apart and still have it easy to see. Because of the 180, it's big, so I want to use a big number. And so if I use x equals 50, I have 180 minus 2 times 50, which is just 80. So as far as our ordered pairs go, we've got a point at 0 and 180, and a point at 50 and 80. Before I draw this line, I'm going to find the points for the second equation as well. just so they're together. And so I've got x, and what was my second equation? Oh yeah, the 100 minus x over 3. Y is 100 minus x over 3. Again, I'm going to use 0. It's a nice number. So then I have 100 minus 0 divided by 3 is 100. And again, 3, it would be nice, right? 3 divided by 3 is 1, and I can deal with that easily, right? But it doesn't help because I've got a huge number to subtract from. So I'm going to pick a little bit of a bigger number, still divisible by 3, right? Maybe something like 30. Stealing from my notes here. Maybe a random number like 30. So we get 100 minus 30 divided by 3 is 90. So our ordered pairs are 0 and 100 and 30, 90. Sometimes what you might find later on is that it might be clever to, well, we use 0 here, right? We force x to be 0 here, but it might be nice if you forced y to be 0 here and kind of did the reverse and solved for x, right? Because then you know where it's crossing both axes, right? And so that might be nice. It's not something I did this on purpose so that we weren't doing that, right? Just to show you how to do it. But sometimes that saves you a little bit of work later on. Yeah. But for now, you can just pick any value of x. Okay, so now we're ready to draw this, and our y-axis, I know, has to go to at least 180, right? And so I'm going to be making each line worth 20 units, right? And so I'm still going to have, what, 9? 1, 2, 3, 4, 5, 6, 7, 8, 9 lines at least, right? So we'll have room for 10 lines of graph. Well, I've got a page break here, but the page break is right here. What do I do now? 1, 2, 3, 4, 5. No, that's not going to work. I want my graph all on the same page, so I'll start here. 1, 2, 3, 4, 5, 6, 7, 8. Go like that. Now remember, because we're drawing these, right, they're not going to be very precise, right? But that's okay. On the test, I'll give you the graph, and then you can just draw it on there, right? So you don't have to do this step, at least. And so using each point as 20, 40, 60, 80, 100, 120, 140, 160, and 180. Doing the same thing over here on the x-axis, I'm going to make each point worth 20, and I have to have at least 100, so I need at least 5 ticks. So 20, 40, 60, 80, 100. Okay. So far, so good. Right now, we've done all the hard work of finding points on the graph, so now we can draw them, right? And so equation 1, we'll start with equation 1. We need a point at 0, 180, and I'm going to use different colors for these just to show it. So at 0, 180, I have a point. My next point is at 50, 80. So 50 and 80. Kind of approximate. So now we're ready to draw this equation number 1. And remember, we just take any straight edge and just connect the dots and extend the line all the way. Okay. And so connect these like so. Now what I like to do, just so I can have these equations on the same graph, is I'm gonna just extend this a little bit longer. Not as nice, but, and I'll say this is equation 1 that has the equation y equals 180 minus 2x. So this is y equals 180 minus 2x. Trying to keep these all on here. Way nicer when we just had x has to be less than 4. Y has to be less than 4. This is more work, but it's the same idea. Okay. So we said, okay, well, we had y is actually less than or equal to 180 minus 2x, right? And so to be less than this line, we have to be in this area, right? And so I'm just going to draw a little arrow kind of saying, hey, down here, that's where I want to be. That's a note to myself, right? That's not something that you have to do. It's just a note to myself for me to keep track of which area I want. All right. Ready to draw the second line on here? Okay. We have a point at 0, 100. So 0, 100. Oh, I guess I should label the zeros. 0, 0. Make it light green. So this is at 0, 100. And the next point is at 30, 90. So I've got 30 and 90 here somewhere. Okay. Got a little crowded in that corner, right? But they're separate lines, so we just keep them separate. And now, ooh. Same idea, right? We're just going to draw this straight line. And so I want to connect these two. Something like that. This example, it got confusing, right? Because this point is so close. But we picked a value of 50 and found 80. We could have said, oh, I want a value of 80. And that point would have been down here, right? So this point, it doesn't matter where it is. It just happens to be close to that intersection. So this is equation 2, and it has the equation y equals 100 minus x over 3. And again, I want everything less than that. So now, it has to be below this line, and it has to be below this line. And that's always going to be the case, right? And so if you're having a hard time with these little arrows, don't worry about it, because another thing that you could do is, like I said, you can just always start here and go until you hit a line, right? Everything inside these bounds are in your feasible set. Okay. And so what we'll do is I'll just shade this in here. Trying to be cool about it. Like that. I'm not going to label it this time, because now you know, yeah. No, because it's not in the feasible set. You mean this part? Because we have to be underneath this line, right? Yeah, so the pink line, but we have to be satisfied both lines, right? And so that's why only this area is in that feasible set, because we have to be below here, right? So we have to be below here, and we have to be below here. Yeah, so here, do you mean this point? Yeah, so we're gonna have to find that intersection. Yeah. All right. So going through our steps here. We go back way, I'll scroll back, you don't have to. We drew the restrictions, we shaded the areas, so that was step 2, we found the feasible set. Well, so step 2, find the feasible set. And I'll just do a little arrow here. Here it is. Or maybe I shouldn't have that arrow. I'll show that that's the feasible set. Otherwise, there's too many lines and things going on. Step 3 is to find all the points of intersection, right? And so what we're going to do is we're going to go ahead and label these. What's a nice nifty color here? Purple. I will always start at the origin, right? A, B. This intersection is the one that we have to solve for, C. And then don't forget about this one down here on the x-axis. That's also an intersection, D. Notice that I haven't paid any attention to the x is greater than 0, y is greater than 0, right? Because that just forces this quadrant, right? And so it's not really that important. It has to be there, but yeah. And so step 3, find all the points of intersection. And so I'm going to list them here. A, I know is 0, 0. B, I also know it's 0, 100. C is the intersection of line 1 and line 2. So I'm going to leave it at that for now and go on and say what D is. But C is the intersection of 1 and 2. Right? And that's when it's nice to have the equations on here, right? The intersection of line 1 and line 2. It's very possible that we could have 3 lines on here, not just 2 lines. We could have a 3rd line. And so then you really want to keep track of, it's the intersection of line 1 and line 2 or line 3, for example. So, and D is the intersection of line 1, right? And y equals 0. Of 1 and y equals 0. Because just like up here, to find these points of intersection, right, we forced x to be 0, right? But if we're going this way, here y is 0, so this line is y equals 0. Okay. All right. So now we're going to find C and D, right? Solve the systems of equations to find the intersections. So solve C. I've got line 1 is y equals 180 minus 2x, and line 2 is y is 100 minus x over 3. What's nice is we don't really, well, we use substitution, but it's easier because they're both in y equals, right? So we can just set them equal to each other, right? Substitute the y from the first one into the y of the second one. And so we get 180 minus 2x is 100 minus x over 3. Yeah. I want to get x on its own, right? Move everything else to one side. And so what I'm going to do is I'm going to move the x's to the left-hand side and everything else to the right-hand side. And so I have negative 2x plus x over 3 is 100 minus 180. We want to collect like terms, right? And so, I mean, you could use your calculator if you want to, but to add these fractions, right, we have to have a common denominator, right? And so we have to multiply negative 2x by 3 over 3 to get it over 3, right? That's multiplying by 1, so it's safe. And so we have negative 2x times 3 over 3 plus x over 3 is negative 80. So then I have negative 6x over 3 plus x over 3 is negative 80. I can combine the top, right? Negative 6x plus x is negative 5x over 3 is negative 180. Multiply both sides by 3. Negative 5x is negative 80 times 3. So negative 5x must be negative 240. X is negative 240 over negative 5. I'm showing a lot of steps, of course, right? But you're always safer the more steps you show. Negative 240 over negative 5, x is 48. Now I know x is 48. Now I can solve for y, right? There's no way I'm using equation 2 because it has a fraction in there, no thanks. But I can use equation 1. So I'm going to substitute x equals 48 into equation 1, which says that y is 180 minus 2x. So y must be 180 minus 2 times 48. 180 minus 96. So y must be 84. Yeah. Yeah. No, so we've got the, are you talking about the inequality switching or the negative? The negative. So you've got this negative here, right? And so this is negative from here, right? And this is negative. Yeah. So you still have to divide both sides by negative 5. Yeah, because it's multiplying here, so you have to divide both sides by negative 5. And then because we've got these two negatives, they cancel out. And that's why it's positive. Oh. So now we know that this point of intersection is when x is 48 and y is 84. It's always a good idea to check your graph to make sure that that makes sense, right? And so let's just check our graph. So we're saying at this point, x is 48, sure, right? And y is 84, sure, right? But we have to do the calculations to know the actual values. You can't use your graph to figure out what those values are, right? You have to do the calculations, right? But looks reasonable given our graph. Right? And so C then is at 4884. Okay. So we solved that one. Now we're going to find the D intersection, our last intersection. But remember, we outlined and said, okay, well, D is just the intersection of equation 1 and y equals 0, right? Because it's crossing the x-axis. And so find D, which is the equation 1, which is y equals 180 minus 2x, and y equals 0. Call this kind of equation 3 for a little bit. Right. So if we substitute y equals 0 into equation 1, right, we have to solve for x. So that's what we're looking for. What's the value of x when y is 0 here? And so we get 0 is 180 minus 2x. Solving for x, I'll pull the 2x to the left-hand side, so I get plus 2x, so 2x is 180. And so x must be 180 divided by 2, so x is 90. So D is at the point 90, and we already know that y is 0 because that's what we forced it to be. Okay. So now, that was what step? I'll have to scroll all the way up here. Hang on. That was step 3, find all the points of intersection. Now we know what all those ordered pairs are. Step 4, make a table of all the ordered pairs. Step 4, make a table of all the intersections. And so we've got intersection A was at 0, 0. B was at 0, 100, right? C we just found was at 48, 84. And D was at 90, 0. This is when we bring in our profit function, right? We've left it alone for so long now, I don't even remember what it is, but luckily I have it here. So the profit was x plus 1.2y. Okay. All right, so now we plug away and calculate. You okay? Oh, it's the worst. It's the worst. We're just going to plug away and find these profits, right? Easy street now. So we've got 0 plus 1.2 times 0 is 0, great. 0 plus 1.2 times 100 is 120. 48 plus 1.2 times 84 is 148.80. I have it here, that's why. Don't worry. And then we've got 90 plus 1.2 times 0, which is 90. We've got a winner, 148.80, right? And so the profit is maximized when x is 48 and y is 84. Therefore, the profit is maximized at 48.84 with a profit of 148.80. I guess I didn't write the step 5. Step 5, calculate the profit. Where do I sneak that in? Here, maybe. Step 5, calculate profit. There. So it's a big problem, but it touches on a lot of things that we've learned, right? Drawing straight lines, solving systems of equations, plugging values into functions, right? All those things we've already learned. And so it just bakes them all together into a nice problem. Okay? But like I said, these are big, right? So you want to go through, and there's some in the textbook that you can go through and try, right? And work through. Yeah.
Is your sept always going to be the biggest number?
Not necessarily, because you could have something like, you could have a line that's like way out here, and then you have a huge X, and maybe that's good. It kind of depends on how your profit function works, right? A lot of the time, yeah, it's that outer corner, but there are rare instances where it's not, but yeah. Cool. Any questions? No? All right. Well, that's all we're doing today. So that's the end of chapter 2. We'll start chapter 3 next day. But make sure you do some practice problems on this stuff, okay? It's hard.